You'd think for how much we actually play with technology, I would have that on grounds by now. Alrighty. So, good evening, y'all. As Renee said, I'm Rachel, and we're gonna talk a little bit tonight about the Red Planet and the Perseverance Rover. So I actually can skip my first few slides because Renee covered it in much more detail than I was going to do. But I will show you a fun picture of my Mars simulation chamber, which is at the University of Arkansas. So it's this picture on the right, and it actually simulates Martian conditions, so it can get down to Martian temperature and pressure and humidity. And then I can change the atmosphere and the humidity to kind of help adjust what conditions I would like to play, whether it's a warm summer's day or a cold winter night, and then see if I can form water on Mars and how long that lasts. So, Mars. So I might be a little biased, but Mars is my favorite planet. It's the fourth planet from the sun, and it's about 4.6 billion years old. A Martian year is about 687 Earth days, and a day on Mars is called a sol. And a Martian sol is 24 hours and 37 minutes. So a little bit longer on Earth, and that's really important when we're having to calculate what's happening on Mars versus here on Earth, because you can't just call it good, you have to do those conversions. So we know a lot about the surface, and we're learning more about the interior thanks to the InSight lander that landed a few years ago. So Mars has two moons. The one on the left is Phobos. He was named after the god of phobias. And Deimos is named after the god of dread and terror. I should also point out that Mars is named after the god of war. So of course, war would have phobias and terror and dread along with them. But both of these moons are captured asteroids that just got caught in Mars's gravity and just now orbit the planet. So Mars's atmosphere is very carbon dioxide rich. It's about 95% carbon dioxide, and then it's got a little bit of nitrogen and argon, about 0.17% oxygen, some carbon monoxide, and a little bit of water vapor. So on Earth, our atmosphere is about 1,000 millibars for atmospheric pressure, and Mars ranges anywhere from 4 to 8 millibars. And this causes some rapid evaporation and sublimation, as well as rapid freezing. But it does have an atmosphere, and so that'll come into play later when we talk about weather. So Mars doesn't have a magnetic sphere or an ozone layer, so radiation does affect the planet. And that's actually a really big thing, a very big worry that NASA has as we talk about sending astronauts to the planet, that there is very little protection from radiation, unlike here where we have our atmosphere and magnetic sphere to protect us. And then Mars does have humidity, and it ranges anywhere from 5% all the way up to 100%. So on some days on Mars, it'll feel like a very hot Arkansas day. So there used to be volcanic activity on Mars. It ranged from about 3.7 billion years ago to just short of 500 million years. And we see this with seeing actual volcanoes, as well as some lava flows and vast lava plains. So the largest volcano, laser pointer, is this one right here. And it's called Olympus Mons. It's actually the largest volcano in the solar system. And it's about 16 miles tall, which is 3 times taller than Mount Everest. So the lava on Mars is very similar to the lava on Earth. It's very basaltic. However, when there are eruptions, it's much more explosive and causes much more ash due to its low gravity. So kind of imagine Mount St. Helens violent eruptions, only on a much larger scale. These volcanoes don't erupt as much as they don't erupt at all anymore, but they don't erupt as much on Mars as they do on Earth, but they are much more violent when they do. So there are 2 other main types or sections of volcanoes on Mars. These right here, which is Thares Montes, and they're 3 large volcanoes, and they're actually the youngest volcanoes on the planet. And then on the exact opposite side is the Elysium volcanoes, and that's another set of 3. So, as I mentioned, Mars does have an atmosphere, and that allows winds to happen. So sometimes these winds can cause localized updrafts called dust devils. And you see these in movies, or if you're in the Southwest and you can just look out into a dusty field and see like a mini volcano of dust. Well, that's what these are, only they're on a much larger scale. They can get to be about 50 times as wide and 10 times as high as the ones on Earth. But what's really cool is they leave these dark trails on the ground, as seen in this far right picture. So we can actually take pictures and track where these dust devils are occurring and be able to study them a little better. But sometimes it's not just a dust devil. Sometimes a larger storm kind of kicks up and causes dust storms. And just like here on Earth, there's some that happen yearly, and then there's some that happen on a more global scale and it's not very localized. And these storms can last a few weeks or they can last longer, and they can reach up to about 60 miles an hour. So a great example of a global dust storm is the one that happened in 2018. So on this bottom picture you see on May 28th, just a normal picture of Mars. You can see its features, some of the poles, and then less than 2 months later on July 1st, you can't see anything due to the extreme amount of dust in the air. And this was actually the storm that killed the Opportunity rover. So wind also plays a role in sand dunes, because as the wind blows, it picks up sand and then it drops them in certain places. And we can tell how the wind is, what wind patterns are happening based on the shape of these sand dunes. And what's cool is we actually see these sand dunes on a ton of different elevations and terrain types. It's not just in one small spot on Mars. And as I said, this helps us kind of understand both the climate and the sedimentary processes, right? Because we can see where the winds weaken and drop, how the winds are flowing by the shape, but we also can kind of see how the sand is being transported on Mars, and we can understand better why we see maybe mineralogy in a certain spot when it shouldn't have any rocks or sand in that area. And we've studied these extensively through rovers and orbiters on Mars. So rocks. I have a lot of knowledge on rocks, and I could write an entire presentation on it, but I tried really hard to contain it to 2 slides. So the main type of rock on Mars is basalt. It's an igneous rock, but we also see sedimentary rocks, which are rocks that weather into other minerals and rocks when exposed to water, wind, and different types of gases, kind of like sandstone and carbonates and stuff like that. So a fun fact, the Opportunity rover actually found that sulfate deposits could contain up to 22% water in its weight. And we see lots of aqueous minerals all over Mars. And that is awesome, right? That proves that there is water, there used to be water on Mars. But what's really cool is they weren't all formed by lakes and rivers and oceans. We actually found some evidence of them coming as hydrothermal fluids, which means hot water was underneath the ground and migrated up to create different minerals. So I wanted to show an example of a few different types of rocks. As I said, we have evidence of igneous and sedimentary rocks, but we have not found any metamorphic rocks on Mars, and we are not sure if they just weren't able to form since they need high heat and pressure, or if there was just no way to get those rocks to the surface for us to be able to see. But on the left side, we have some igneous rocks, and the top one is scoria, and then the bottom left is a basalt column. And since that image was a little blurry, I decided to show you one on Earth just to show you what they kind of look like. And then on the right, we have sandstone, mudstone, and shale. Right, so I mentioned that there used to be water on Mars. And in fact, in 2010, we'd been able to map 40,000 different river valleys. And we see 2 types of rivers on Mars. We see the very branched ones where if you would look at a map, they just couldn't pick and they fork this way and that. And then we see the super long single flows that just kind of look like a serpent going down on Mars. And so the Curiosity rover actually found direct evidence of an ancient stream bed while it was roving around in Gale Crater. And it actually was able to identify that the water was about hip deep and it ran at about 0.2 meters per second. We were able to determine that based on some of the rounded pebbles and gravel fragments that could only be formed by super strong currents. So here are a few pictures of evidence of ancient water on Mars. On this right picture, you could see, as I was talking about, the super branched river channel, right, where it just can't pick a way to go. And then on the left, we see a river delta. which you see similar here on Earth, right? The Mississippi River Delta is a great one where basically debris has been traveling down the river and then gets deposited in a large body of water, creating these really beautiful delta fans. So obviously Mars used to be very wet and warm, but now it's kind of cold and dry and just kind of meh, right? And so what happened? Well, part of it could have been caused due to its loss of atmosphere. As I said, it doesn't have the protection Earth has. So the solar winds and radiations could have caused some of the atmosphere to deteriorate, which then would change the climate. But also in general, Mars just faces climate change just like we do here on Earth. Mars has a larger axial tilt that changes over time, and it also changes orbit just like Earth. And so some days it's a little closer to the sun and sometimes it's further away. And so those also can contribute to the changes in climate, taking it from that really wet and warm, fun environment to this cold and barren one. But what's cool is we still see evidence of climate change today. And a great example of that is at the South Pole, where we're seeing some warming and the CO2 ice is sublimating away. But just because it's cold and dry doesn't mean there isn't water on Mars today. So we actually have some water still at the surface. Most of it is at the poles. And then there's sparse liquid elsewhere, and then a lot in the near subsurface, and that includes things like the ice tables and ground ice and glaciers and reoccurring slope lineae. So this bottom left picture is a picture of our North Pole, well, their North Pole, and it's composed of water and CO2 ice. The middle picture is evidence that a glacier had traveled through there, and it's called a deposit lobe, whereas the glacier kind of pushes and travels along, it deposits out rocks and dirt that it brings along the way. And the right picture is an image from the Phoenix landing site. So Phoenix was a lander that landed in 2008 on Mars, and it had a little shovel tool. And as it dug deep into the surface of Mars with its first shovel scoop, it was able to see these bright white spots. And that actually is ground ice just a few centimeters below the surface. So we have a lot of rovers and orbiters around Mars. And the Mars Odyssey orbiter was able to detect large amounts of surface hydrogen that are seen globally around Mars. And if you were to look at a map, basically anything below 60 degrees of latitude, you can see ices in small patches in a few regions, like the Elysium volcanoes. And this ice can be up to 18% in concentration in these little blocks. But above 60 degrees, ice is really abundant. It exceeds almost 25% almost everywhere above 60 degrees. And as you approach the poles, it actually gets to 100%. And as I said, we have quite a few orbiters who have already helped identify this. But because the atmosphere is very unstable on Mars, the ice isn't able to last super long if it was just on the surface. So most of it is covered by a thin layer of rock or dust material to help keep that ice from sublimating away. We also have ground ice. And so one way of this is in permafrost regions, kind of like in the northern Arctic. And what happens is it creates these patterns on the ground called polygons or patterned ground. And it basically is as the ground freezes and thaws, it cracks the ground around it, creating these really cool patterns on the ground. We also have evidence of spots where there's large slopes on Mars and there's exposed water sheets there. And some of those can be up to 100 meters thick, but they'll be covered by a layer of 1 meter or 2 thick of soil. So fun fact, you can find shallow ground ice at roughly 1/3 of all places on Mars. And an extra fun fact, if you were to absolutely melt all of the ground ice that is on Mars, you would cover the entire planet with 115 feet of water. So I wanted to show you an example of patterned ice. So this left picture is a more zoomed out picture, but you can see that there are cracks everywhere. And when you zoom in, you can actually see where the ice is filled in those cracks that have been split. Another example of ground ice is when craters impact, it can kick up dust in the area, exposing ice. And so here you see a crater that had been recently formed, exposing some water ice. And then a little while later, you see that it's starting to disappear, but there is still some on the surface. So just like on Earth, the poles grow thicker during the winter and partially sublime in the summertime. And the South Pole is the larger of the poles and has more ice. In fact, this ice can go 2.3 miles below the surface. That's how thick it is. And the South Pole is basically broken into 3 sections. There's the very middle part, and it's super bright in the images, which I'll show you in a second. And it is mainly carbon dioxide ice with about 15% water. And then the second part are more on these steep slopes, and they're called scarps, and they're made almost entirely up of water ice. As you go further away from the polar cap, you see more of these scarps fade into a plain area, which is the third part, which is basically kilometers and kilometers of just the permafrost and polygon regions. So, fun fact, if you melted all of the ice at the South Pole, it would cover the entire planet with 36 feet of water. So, as I said, quite a bit. So, on the left is a picture of the North Pole again. And on the right is a picture of the South Pole. So this little region right here is that first layer that's mainly carbon dioxide. And then you see these that are more of the scarp regions, which are almost all made of water ice. And then this area here, which you can't super see any patterned ground, but that's that permafrost region. Turn off. Haha. Okay, so another place that we might see water on the surface are in a place called reoccurring slope lineae. And so basically there are these slopes that are on, when they face the sun, create dark streaks. So during the spring, we start to see these darkened long streaks that kind of look like wet soil. And as it gets more into summer, they actually get darker and longer, and then they fade away in autumn. But then in the spring, they come back. And there are some theories on whether this is made and created by water or if it is a dry soil movement. And I have actually yet to meet a Martian scientist who does not have a very strong opinion one way or the other on this. But it is not for sure yet what actually is causing them. But they are fairly abundant, as seen in this bottom right image. So this is part of Valles Marineris, which is a very large canyon on Mars. And every single one of those blue dots is a spot where we've seen some of these RSLs. So Mars has a bunch of other cool features, and I kind of wanted to show you 3 of my favorite. So this far left one here are called Martian blueberries. And basically when water used to be on Mars, there was minerals floating around in that water. And so some of them would start to stick together and condense and create balls. These are made of iron and hematite. And basically these heavy iron balls would fall to the bottom of the ocean or the water. And then even though the water is gone, they remain. And so there's just these little balls of iron and hematite on the surface of Mars. And in this upper right image, these are called Martian spiders, and this is a type of permafrost patterned ground. And so just like before, the freezing and the thawing of the ground actually cracks it. This is taken during the summer, so there is not ice in these cracks at the moment. And then this bottom image is an image called Swiss cheese. And we see this Swiss cheese on the South Pole. And so these divots are actually holes in the ground, and they're formed of CO2 ice. And so over time, as the CO2 ice starts to sublimate away due to warmer weather, you can actually see them grow in size. So this is a great way to track some of the climate change and warming that is happening on the surface. So, as I said, we know a lot about Mars, and that's mainly due to a lot of the rovers and landers and orbiters that we have sent. So here's a picture of Mars's family portrait. And Perseverance is about to join this family. So Perseverance launched on July 30th, 2020 out of Cape Canaveral Air Force Station, which is in Florida, aboard an Atlas V rocket. And it is going to land next week on February 18th around 2:55 our time. It's going to be about 1.5 year mission, Martian years, and is launched with an instrument called Ingenuity, which we'll talk about later. So what is Perseverance? Well, Percy is about the size of a car, and it is a rover that will drive around on Mars. She is about 10 feet long, not including the arm, which is another 7 feet, 9 feet wide, 7 feet tall, and she weighs about 2,260 pounds. And you'll notice that I'm referring to Percy as a female. And that is because space, as well as the planets and the moon, are under international water laws. And so because it is under international water laws, all rovers and landers are seen more as ships. And so the ships were named after females in the past. And so all of the landers are considered female. So Percy, or Perseverance, is basically the same model as the Curiosity rover that landed a few years ago on Mars, with some new improvements. One of the big ones is the wheels. So Curiosity's wheels have been very torn up by the rocks. There's also been times where it just couldn't get enough traction as it was trying to drive on the very silty and loose regolith of Mars. And so Perseverance has some new and improved wheels. They're a little bit more narrow than Curiosity's, but they have a lot more treads and they're much more sturdy. So hopefully they will not get beaten up as much. Also, they have different instruments on the arm, as well as the arm is different because it had to be modified for the instruments that Perseverance was bringing. So Percy is run and energized by a multi-mission radioscopic thermoelectric generator, or an MMRTG. But basically, it is a box of plutonium that is naturally radioactive and decaying, and this decay causes heat, and we're able to turn this heat into electricity with its two batteries. And so these batteries and this electricity will be able to power the rover and all of its instruments, as well as keep it warm in the winter nights, right? Because a night on Mars gets cold and it can actually get to negative 130 degrees Fahrenheit. So super cold, and we'd like it not to freeze. But what's cool about this MMRTG is it has a lifespan of 14 years. So even though Percy's main mission is not going to be that long, hopefully it'll be able to go long past the initial mission and continue to keep doing work and science. So Perseverance has 4 main science objectives. One is geology and to study all the rocks, because why wouldn't you study all the rocks? But it also wants to learn the history of Jezero Crater, which is where it'll be landing. It also has a very strong astrobiological side. It is looking for evidence of past life. And this means looking for the physical evidence of life, but also just to see if the environment could even host life, right? We may get there and be like, oh man, we did not anticipate it to be this harsh. And so it's going to look for some of those key points as well. It'll also have a sample caching section where it will collect and prepare samples. And then it'll also prepare for humans, right, by testing different types of technology that will hopefully help astronauts in the future. So the big thing that sets Perseverance apart from every other rover we've sent is it is going to collect samples. So Perseverance has a bunch of different drill bits that are on this arm, and it has a rack holding 43 test tubes in the belly of Perseverance in this little blue circle. 5 of those are going to be tubes that are just helping for calibration. So we are hoping to collect up to 38 samples. And so what will happen is Perseverance will drill a core sample into the dirt or a rock and go about 2 inches deep. And then it'll collect a sample into this tube and store it. And these samples are going to be very small. They're only going to weigh about a ½ ounce or 15 grams. So that's roughly the weight of a CD or 3 pieces of computer paper. So once the sample is collected, it'll be sealed and stored on board the rack that is right there in that little circle. And it'll kind of just chill in the belly of Percy until NASA finds a place or places it would like to deposit these samples. And then it'll take lots of pictures of that area and it'll geomark it so we know where we're leaving them, but we will leave these test tubes on the surface, which will hopefully then be picked up with future missions to be brought back to Earth for us to study them. Scroll. Okay, so Perseverance has a lot of cameras. In fact, it has 23. Some of these cameras are to help with descent and landing, while others are more engineering based, right? So you have some navigation cameras or nav cams that are going to help with navigation. This is especially important because Percy is a self-driving rover. The communication between Earth and Mars is a little lagging, It changes, but based on the positions, it can be anywhere from 5 to 20 minutes. And so we can expect Houston to basically give it step-by-step instructions every step of the way. And so Percy is a smart driving vehicle, and it's going to drive on its own. Along with the help of its nav cams, it's also going to have hazard cams, which will help detect for hazards like rocks and trenches, right? So that way Percy doesn't drive in a ditch and then the mission's kind of over. There's also going to be a camera called the cache cam, which its sole job is to look at the samples being collected and put into the tubes. And this will help the scientists who will later be studying these samples so we can go back and see exactly what the rock looked like as it was being drilled, where it was located, and all of that fun jazz. There are also 5 different types of science cameras. So the first camera is Maz-Cam Z, and it's actually 2 cameras. And these are the really pretty cameras. They're the ones that are going to take everything in color. They're going to create all the 3D images. And it has a super powerful zoom. And I mean super powerful. It can zoom in to about the size of a horsefly from the distance of a soccer field. And Maz-Cam Z was going to help pick out some of the best rocks for us to take samples of and to study, as well as to help hunt for some terrain that might have signs of life or water. The next one is called SuperCam, and SuperCam is going to fire a laser at mineral targets and then analyze that vaporized rock. And so what SuperCam does is it fires laser pulses at a super small area, about the size of a pencil point, and it can do this from about 20 feet away. And once the rock is vaporized, we will be able to analyze the hot gas and everything in the gas to break down exactly the mineralogy and chemistry of what we just destroyed to figure out exactly what that rock was. The next one is called Pixel, or the Planetary Instrument of X-ray Lithochemistry, and it uses X-ray fluorescence to identify chemical elements, and these elements can be about the size of a grain of table salt. It also contains a camera that takes close-up pictures of rocks and soil textures. So the next set of cameras is a pair set. It's Sherlock and Watson. So Sherlock stands for the Scanning Habitable Environments with Raman and Luminescent Science of Organics and Chemicals. But that's a mouthful, and so we called it Sherlock. And Sherlock is using spectrometers, a laser, and a camera to mainly search for organics and minerals that have been primarily found in altered water environments and signs of microbial life. So Sherlock has a magnifying glass, just like our fictional character Sherlock Holmes, and it uses an ultraviolet laser light to spot organic chemicals, much the same way that crime scene forensics and investigators use now to look for clues. Sherlock also carries a really small piece of spacesuit that is right here, and this is one to help with calibration, but it is also to just kind of see how a spacesuit can hold up against the harsh Martian environment. Now, just like in the real Sherlock and Watson environment, as Sherlock is over there super analyzing everything with a microscope and getting lost in its fine details, you need someone to get the larger context, and that's what Watson does. So Watson captures the larger context of all the images that Sherlock is super analyzing. It'll help provide some of the fine scale textures and structures of that rock and dust. But Watson is also on the arm in a spot that it can move. And so it can actually go and take pictures of other rover parts to see if something isn't working, as well as help look for some geological targets. But there aren't just cameras on this rover, there are also science instruments. And one of them is MITA, or the Mars Environmental Dynamic Analyzer. And MITA takes weather measurements. It takes wind direction and speed, as well as temperature and humidity. And it'll also help measure the amount of dust in the atmosphere and what size that dust is. And so this is useful for quite a few reasons, and it's not just to help the astronauts later on know what type of weather they may be experiencing, but it can also tell us things like how much water vapor is being exchanged into the regolith from the atmosphere, so we can determine how much of that water might actually just be absorbed into the dirt. We can also see how much radiation from the sun and space are helping to alter those rocks and dirt. The next one is called MOXIE, or the Mars Oxygen In Situ Resource Utilization Experiment. And MOXIE's main job is to produce oxygen from this super rich carbon dioxide atmosphere, right? As I said, it was about 95% carbon dioxide. And so MOXIE is going to inhale carbon dioxide and exhale oxygen, kind of like a tree. And this has two goals. It's one to help us just kind of understand our limits for creating oxygen, which would then help astronauts maybe have breathable air. But it's also to see how much propellant we can create. So, fun fact, rockets are going to need about 33 to 50 tons of fuel to launch off the surface of Mars. And hopefully this homemade supply can provide 3/4 of that. And the reason this is so important is that is a lot of weight to send from Earth to Mars. And not only does that take up a lot of space, it's really expensive. So if we could create this on Mars, we could then save all of that room and all of that for other things like new science experiments or maybe even astronauts. So right now, MOXIE is about the size of a car battery, but hopefully in the future, these will be about 100 times larger, and there'll be more than one of them so we can help produce some of this oxygen. So the next instrument is called Rimfax, or the radar imager of Mars's subsurface experiment. And basically it is a ground penetrating radar that is attached to the bottom back of Perseverance. And it is basically going to send radar waves into the ground to see what's underneath the surface. And so it'll see different geological features, as well as be able to detect ice, water, and salty brines more than 30 feet below the surface. Also, fun fact, this is the first radar tool that has been sent to the surface of Mars. So, Percy, as I mentioned, is having some lag time, right, between 5 and 20 minutes. And so we're going to need different types of antennas to be the voice and the ears for this rover. And so one of the antennas is the ultra high frequency antenna. And it basically transmits data to Earth through the Mars orbiters. So it'll send its data up to all of the orbiters orbiting around Mars and then send it to Earth. And it can send lots of data. It sends up to 2 megabits per second. Then the next one is the X-band high gain antenna. And this is a movable antenna that transmits data directly to and from Earth. So not only can it talk to Earth, but it also can receive stuff. And this is about 160 to 500 bits per second in data that can be sent or received. And then the X-band low gain antenna is a non-movable antenna that is only its ears. It can only receive signals and data from Earth, and it's only about 10 bits per second. So next week, Perseverance is going to land on Mars. But before it lands, it's going to experience something called 7 minutes of terror. And this has been nicknamed that due to its lack of communication, right? We won't even necessarily know it lands exactly when it lands because it will take a little bit to still transmit that. But what'll happen, it'll cause an initial descent of going over 12,000 miles per hour, but a heat shield is going to slow it down, and then a parachute and then a powered descent is going to slow the rover down even more to allow this sky crane to lower Percy to the surface. And it'll land, as I said, around 2:55 our time. But I kind of want to walk through this process a little more about what's going to happen. So let me turn on my laser pointer. So basically, you have Perseverance inside here, and as it enters the atmosphere, it's going to reach speeds of 12,500 miles an hour. And this heat shield is going to help slow it down quite a bit, and that heat shield's going to get hot. It's going to get 2,370 degrees Fahrenheit. But the good news is the heat shield's going to do its job, and Percy shouldn't reach temperatures more than room temperature. Once we get about 4 minutes in, we're going to deploy this very large parachute. It's 70 feet in diameter, and that's going to help slow the rover down from roughly 940 miles an hour all the way down to 200. And so once the parachute deploys, we're going to drop off the heat shield, and this is going to allow us to start using those cameras that we have for landing and descent. It is also going to use an instrument called range trigger, which is going to help determine how far away they are from the landing zone and to start looking for some major hazards so we don't land in a place we don't want to. Just short of 6 minutes, we're going to lose our parachute and our back shell, and we're going to drop Perseverance in this power descent vehicle. And this power descent vehicle has 4 different little boosters that's going to slow down the descent even faster. And so it's going to slow it from about 200 miles per hour to 1.7. And 12 seconds before it reaches the ground, it is going to hover about 66 feet off the ground and use 3 cables attached to Perseverance to slowly lower Percy to the ground. Once Percy lands safe and sound, the cables will disconnect and then it'll fly away so that it can crash land somewhere that isn't going to interfere with the rover. Turn off. Okay, so there is an instrument on the belly of Perseverance that is going to be released once Percy is safe and sound, and that is called Ingenuity. And Ingenuity is a helicopter that weighs less than 4 pounds, and it is going to be used to test flight on Mars, which is something that has never happened before. And so over a span of 30 sols, it's going to conduct a series of test flights starting mid-spring this year. And the goal is for it to fly about 10 to 15 feet off the ground for up to 90 seconds and travel distances about 980 feet at a max. And I know a minute and a half doesn't sound very impressive, but I'd like to remind you that the Wright brothers, when they had their first flight, lasted only 12 seconds. So 90 seconds is starting to sound pretty good. And so as it's flying, it has sensors to collect data and speed and direction. And the brain, or the aviotics, which is in this little square area, is basically the brain and helps it function and navigate. And this is super important because it flies on its own. Due to the lovely lack of communication and the lag time, basically Houston's going to be like, you fly now, and then Ingenuity is going to have to do all of the rest. And so this body is insulated and has heaters to help keep everything warm so that it doesn't freeze at night, and it's solar power charged. And these blades, just for reference, are about 4 feet long and they're made of a carbon fiber foam core. So Perseverance lands. Well, where is Percy even landing? So here's a map of Mars, and it's marked with all of the rovers and landers that we have landed. And so you'll see here that Perseverance is in this section that's not been explored before, and it's going to land in a spot called Jezero Crater. And Jezero Crater is a large impact crater. It's about 28 miles long, and it's about 3.56 billion years old. It used to be a lake, and it actually has an inflow channel and an outflow channel. So you can see up here in this big image, you can see where the river kind of flows in. And then there's the big lake, and then there's an outflow channel on the other side. And what's really nice about Jezero, it has a beautiful, beautiful delta, and a lot of different and diverse mineralogy had been brought in by that river. So when NASA was looking at the Mars 2020 rover, which is what this used to be called before we decided on Perseverance, we had quite a few spots that we were looking at. And Jezero was selected because it was one of the best, if not the best, chances of finding evidence of life on Mars. So if life existed, this is probably one of the best spots to find that evidence. And so Perseverance is going to be landing, hopefully, in this little oval right here. And it's about 4.8 miles long by 4.1 miles. And then once Percy lands on the surface, NASA will finalize the game plan of where Jezero will travel. Because if Percy lands right here, the path of what samples to collect is different than if Percy lands over here. So, as I said, I was talking about potential for life on Mars. And this is the first rover to look for signs of life on Mars. But it's not going to be looking for these big-brained aliens. It's going to be really looking for more microbial life. It'll be looking for traces of fossils, as well as mineralogy and organic traces, just to see if there's any identifying markers that life could have existed there. And it'll also just help analyze the surrounding area to see if this was even an environment that could have had it. But no matter what, this information is going to super help scientists on Earth tweak our stuff, right? So we have scientists doing experiments, as well as models that we're examining every little bit of what could have happened in the past and happening now. And so with this new data, we'll be able to tweak our experiments and our models to kind of better examine what happened or is happening on Mars. So to kind of summarize, Perseverance is a 3-year-long Earth mission, and it's mainly focused on looking for evidence of past life on Mars, as well as to study the environment of an ancient delta, while collecting diverse samples that will hopefully be returned to Earth in the future, as well as test the ability to create oxygen out of the very CO2-rich atmosphere. It is also bringing Ingenuity along for the ride, and Ingenuity will be the first thing to attempt flight on Mars. And with that, I thank you, and I will take any questions.
Thank you, Rachel. This is very informative. I've got a few questions that I will happily start off with, and then anyone else, please, if you have any questions, just use the chat feature and I'll relay those. I guess you said that the rover has, you were describing the battery life or the life of the rover. How long do you think the mission or the rover is going to last? I mean, how long do you think it will be collecting samples and stuff?
I'd like to tell you 14 years. That's obviously our hope. This is obviously, by using this type of power, we've eliminated the situation that happened with Opportunity, where the global dust storm just killed its solar powered batteries and they weren't able to revive. You know, we would like it not to drive into a ditch, because if it drives in a ditch, it kind of, you know, messes up the plan a bit. But I think it has the potential to do the 14-year mission.
Okay. I know you have mentioned that, but I didn't know what the, you know, the specs or the goal, you know, the goal was. I am very curious about Martian blueberries. Yeah. How big are those? I've never heard of such a thing.
That big at a max. They're super tiny. They're adorable. Then we have these here on Earth as well. Oh no, they are not in my rock collection behind me. They must be in my office, or else I would have shown you an example of one.
That's amazing. And you know, they're made, you said they're made of iron and
hematite.
Okay.
Yep. And that's what also gives Mars its red color, because the iron causes that rust color, which then affects the dirt.
Okay, thank you. Ever since you showed that picture and talked about it, I was like, whoa, wonder how, you can't tell from the picture. It's like, I wonder how big those are. So like a marble, or basically, just a little bit bigger than a blueberry, depending on how big those get. Okay, thank you. Thank you for that. Now the rover is going to land a week from today.
Yes.
And is there a way, you know, this is of course, has been in the news a lot, you know, leading up to the landing, and what is the best way to get the most recent updates and information about how the landing goes and how it went, and then yay, you know, we made it, or what's the best way to keep track of that?
Well, there's two ways. The first way is JPL, which is the one hosting this mission, is going to have a live stream basically all day. They will be interviewing scientists and sharing their knowledge. The other one is the Green Bank Observatory, which is in West Virginia, is a very, very large radio telescope. And so the GBT telescope will actually be able to identify that Percy landed first before we receive the communications. And so they will also be live streaming all day and having talks and interviews. But either one of them will happily track. JPL will have a much more extensive list of interviews, though.
Okay, so then as the data starts coming in and we're receiving information from the rover, is that also the best way to you know, keep updated on what it's doing?
Yeah, so JPL updates constantly. Perseverance has multiple Twitter accounts as well. So they also will happily keep you updated, some with a little bit more sarcasm from the rovers, some with just giving pretty pictures. But JPL itself will constantly be pushing out new data.
Okay, thank you. Because, like I said, it's all in the news now, and then it will land next week. And then it's like, well, then, how are we going to keep up with what's happening or just check in? So that's good to know. They've got those different avenues.
Oh, yes.
For
The
us
rovers all have their own Instagrams and Twitters and Facebooks.
Yeah.
And then there's a few more sarcastic, Percy the Sarcastic Rover will still give you a bunch of information, but in a different light, we'll call it.
With just a little different voice to it. Yeah.
Exactly.
Okay. All right. And I have to ask, being a librarian, did you read the book, The Martian by Andy Weir?
Not only did I read it, but when I worked at NASA at my internship, I got to meet the author and talk the science with him.
Oh, wow. Cool. So what did you think of the book and or the movie?
I liked them. It was very scientifically accurate for the most part. He put a lot of research in. Although I will say he learned afterwards that the winds cannot get as strong as they were depicted in the movie, and he wishes he would have actually added in lightning because there can be lightning on Mars, and he thought that would have been a fun way, but it was a little too late to start tweaking it.
That's okay. I mean, it seemed like there was a lot of research
very much
that had gone into it, and my cat's attacking me. Hold on. So that's good. And but still, it is a work of fiction. So it's okay that the lightning wasn't in there. The wind speeds were off a little bit. So that's okay. And you had a slide. You showed a slide about the different missions and rovers and landers and orbiters. What was the first mission that went to Mars, or rover, I guess? What was the first rover, and when did it get to Mars?
Well, yes. So the first rovers were the Viking rovers, and I believe they were in the 80s.
Okay.
Wish I knew the specific date, but
both of the 80s, that's
cool. Year apart in the 80s.
Okay, so it's been, they've been sending different vehicles for decades.
Yes, and many other countries have as well. I don't know if you guys have been watching the news, but yesterday the Hope orbiter actually entered Mars's atmosphere, and so the UAE became the 5th country to reach Mars. And then this morning, the Chinese orbiter Taiwan-1 also reached the orbit of Mars. And so they will be hopefully putting a rover in May, June to the surface. So it's going to circle Mars for a bit. And once it finds a spot it would like to land, it will deploy the rover. And that rover also has a ground penetrating radar unit on it.
Okay. Okay. Let's see. I had another question too. I can't think of it right now. I should have written it down.
It's all good. It'll come to you.
Yeah, it will. It will when we get signed off. I'll email you.
Perfect.
Does anybody have any questions that they'd like to put in the chat before we start to wind things down? Oh, I know what it was. It was, when is the next mission, whether it be a orbiter, lander, rover, whatever? Do you know when that is slated to happen?
They have not finalized anything yet.
Okay.
They have plans and they're working on designs, but they have not set dates yet.
Okay. All right. Thank you. Thank you. There's a lot going on. There's a lot going on right now with these other countries that have sent rovers also. Do they have the same kind of goals as the Perseverance rover? No. Or are they doing something completely different?
No. So Hope is just an orbiter, and it's going to take weather measurements. It's going to do a lot of weather analysis in the atmosphere.
Okay.
And then Taiwan-1, which they have not, I do not recall the name of their rover. I don't know if they've actually announced it. We'll be looking at some ground penetrating radar, and they're looking more at like ice.
Okay.
So not exactly the same, but all still ties together.
Okay, great. Great. Thank you so much. This is going to help us really be prepared for next week. So glad that we had the foresight to get you scheduled to come in. It's going to be in the news, and we'll be sure to keep an eye on things, not just next week, but afterwards. So if we don't have any other questions, or Rachel, if you don't have any other comments or anything else to add, I'll go ahead and wrap things up for this evening with a final thank you. We really appreciate you being here and educating us on this.
No, I love talking about this stuff, so thank you for having me. It lets me nerd out and share all my fun facts to like other people than not just my close friends. So yeah.
Well, we loved it. I loved it. And I'll talk to you again soon, I hope, and best of luck with everything. Thank you.
Thank you. And thank you guys for spending your cold Wednesday with me.
Yeah. All right. Thank you. And goodbye, everyone. Thanks for being here and joining us tonight. Bye-bye.
Thank you, Renee.
Uh-huh.